Oh. Okay, so what we always want to do, and oh my god, just have to mute myself here. We want to solve a problem, and a really particular problem from topology. This is which groups can act freely on spheres. So we're going to be asking ourselves about topological actions. So saying let G be a group. Oh god, it's lagging so hard. Can you read this? Can you read it? Okay. Because this drawing pad is somehow lagging. I can only see what I'm writing 2 seconds after I'm writing it. Okay. And we say that G acts freely on a space X if each group element is actually just a map from the space to itself. So if every group element admits a map phi G from X to X with the following properties. The first property is that the neutral element, I'm going to write it as 1 times X, so always just X. And we have G times some other element, G of X is just we multiply the group elements together, and this is just an action. Yeah, I'm searching that right now. This is the thing I want to write. You mean with a keyboard, right? Yes, this is exactly what I'm looking for. No, this thing just wants me to either draw or write. Let me see if I can get another program up. I think I'll just use Dropit then. Can I write here? Yes, I can write here. Okay, so let me switch really quick. Okay, can you see this one? Okay. So what we need is, I'm just going to go through the terminology real quick. What is a free action? A group G acts freely on a space X if each G in G admits a map. I'm going to call this FG from X to X with the following properties. First, F1 of X is always X, and Fg of Fh of X just Fgh of X. And the free action means that if G is not 1, then Fg of X is never equal to X. So which means the only map that actually has a fixed point is just the map that is induced by the neutral element. And we want to ask ourselves which finite groups can act on a sphere. Should I go over homology real quick? I think I can just assume it. But one thing we will need is a special space. That space is called BG, called the classifying space of group G. It is a space with a pretty strong property. Namely, it is a CW complex. I'm not going to go into detail what this means, but we're just going to say it is a nice space. Fundamental group G and other homotopy groups trivial. Some examples. Let's see if this works. The simplest group we can think of is just a trivial group. So B of, say, the trivial group, we're just going to call it 1. It's just a point space. And for example, the classifying space of the integers is S1. Or the classifying space of Z mod 2Z is RP infinity. These are just some nice examples. And in order to solve this problem, we want to look at what this classifying space looks like. So what does this mean? This classifying space is unique up to homotopy, and we want to look at if group G acts on a sphere, then we also want some information about what the space BG looks like, and this in turn tells us what the group G looks like. And this is what our final goal is, to look at which groups can act on a sphere. We're going to get some necessary conditions, but not some sufficient conditions. This is an open problem, by the way. If you know from topology what homology is, I'm just going to define this real quick. We can define homology for spaces, but we want to define homology for groups now. And what a homology of a group means is just the homology of this classifying space BG. So we say, oh god, this is big. We'll say that the homology of some group G in some coefficients, I just call them Z now. We define them just to be the homology of the classifying space of G. And we know what this looks like if we know some topology, but we don't know what this looks like. If there are some questions yet. What? No questions yet? No, I can't find any. Okay. Okay, there's some other important space we need to look at. It's called the universal cover. And we're just going to write this as EG. EG is the universal cover of BG. If you don't know what the universal cover is, it is a contractible covering space, a regular covering space. And we're going to look at this homology first. There's a standard model for this space. And the standard model is actually what allows us to calculate such group homology. I'm going to make this bigger. Okay, there is actually a standard model of EG. And if some of you know the category theory, and we have an easy answer, it is the nerve space of G as a category. Okay, this is a really stupid definition in my opinion, but I can show you what it actually looks like. We'll answer, we build a simplicial complex inductively. So we're going to write this as X0 is just G as a group, as a set. And we're going to define X1 as G squared as a set. And so on. What we're doing is we're just going to call Xn. It's just the set of all n plus 1 tuples G with some boundary map. I'm not going to define this boundary map, but oh god, what now? Because it's hard to write down. But we're just going to, I'm just going to say that this is basically just the simplex with G elements. So if G is a finite set, let's say G is some group with 8 elements, then this is just a simplex with 8 vertices. And if this is an infinite set, this is still kind of an infinite analog of a simplex. But the important thing is that this is still contractible. And now, what does BG look like from EG? EG is just EG divided by the G action. What does this mean? We just glue together all points that look something like this. If we have a point that is some G1, for some Gn, we're going to glue this with some HG1, HGN, where H is any group element. We're going to glue all these possible combinations, and we get BG. I'm not going to prove that this is actually a classifying space, but this is what we get. But this is actually really hard to calculate in general. If you have some infinite group, this is kind of not even infeasible, it's just in general impossible to calculate some homologies of this. So we want to see what actually happens here. So what actually happens is the following. To calculate the homology of BG, we have to look at chain complexes EG, and then we want to see what actually happens when we go down through the quotient to BG. So when we divide the G action. And from the standard model that I just defined here of EG, we can actually have a really simple chain complex of EG. And it looks something like this. I'm going to call it standard chain complex EG. Hey, what does this look like? This is just what you just said. Is some ZG to the n, all n tuples, and the three groups that is generated by it. And we go down through our boundary maps. And we go down even more into ZG, and then into 0. This is what our chain complex looks like. Actually, this goes into Z and then into 0. But what is the important thing about this? The important thing about this is that EG is contractible. And if EG is contractible, then its homology has to be 0, so this chain complex has to be an exact sequence. This has to be an exact sequence, and by dividing out the G action out of this chain complex, we obtain a chain complex of BG and then the homology of G. This is pretty hard to swallow. I'm just going to check for any questions now. Muffin. Oh, well, yeah. The problem is that I can't draw like this because I see what I draw after like 2 or 3 seconds, so it looks horrible. But I hope even if this is not text, you can actually see what I'm doing here. And this is kind of a good way to calculate some homology. You can actually calculate some low-dimensional homology from it, but it's not perfect yet. What we actually want to do is really get the essence of it. Which properties of this exact sequence actually make it produce group homology if you divide the G action of it. And what actually happens is that these are all G modules. So a G module is just a module over the ring ZG. So the ring ZG is a free group with a basis consisting of all elements G with the obvious multiplication. What does this multiplication look like? We have some CG times some, I don't know, YH. This is just GH. The exact sequence above is an exact sequence, not just of groups, homomorphisms of this kind. of ZG module homomorphisms. And this is what's actually important here. So we're going to define group homology from this. The new definition that doesn't need any topology now so let G be a group, and I'm just going to call this F. Let F be any exact sequence of ZG module homomorphisms. And we need one more property, is that it ends with Z and then 0. So it has to be some sequence that looks like this, Z and then goes to 0. Then we define the group homology, HGZ, as the homology of F after we divide the G action. Some problems here. The first problem is this actually the same as the homology of BG? Okay, this question we have just answered because we have built a chain complex that is just of this kind. We see that this can in fact get the right homology, but this is the problem number 2. The problem number 2 is this independent of the choice of the exact sequence? This is a really tough question, but it has an answer, and this is called the fundamental lemma of homological algebra. Yes, the homology is independent of the choice of F. This is actually a pretty strong statement. The statement is actually the following. F is unique up to homotopy equivalence. So in a kind of homological sense, there's only one such exact sequence, and all the others are just some squished version of this. By the way, such an exact sequence has a name. It's called a resolution. We call such an exact sequence a resolution of Z over ZG. The resolution of Z means that it ends in Z, and that the resolution is over ZG means is that it's all ZG module homomorphisms. Yes, I wanted to leave this out. This fundamental lemma of homological algebra is only true if we have some other properties, but I don't want to call them yet. This is only true for projective resolutions. So projective resolutions are unique up to homotopy equivalence. But I don't want to go into detail now, but kind of all the resolutions you can kind of think of with the obvious modules will be projective. It's actually not that easy or not that obvious with the groups you know to construct a resolution that is not projective. Any questions so far? Okay. So the question is basically, what does F divided by G look like? That's the question? Okay, so if I write this F as a chain complex, as for example some I, and that goes to some Fi minus 1, and that goes into 0, which we said is Z, G. And that goes into Z, and that goes into 0. Then the chain complex F of G looks like termwise dividing by the G action. And this ends in F0 divided by Z. This is just Z, and the last Z we just throw away and write a 0 here. So this Z is just F0 divided by G. This is what this chain complex looks like. And this only gives homology and coefficiency. We have to do one more thing to get the other coefficients. In some G module M, for example, we do some other thing. We define the homology of G in this module M. For what? We first tensor this chain complex with M, and then we divide the G action out of this. And this is what gets us the homology and coefficients M. And this is actually what happens on the topological level. If you have some coefficient module, then if you write down the chain complex of EG and divide by the G action, this is exactly what happens. So this is actually the same as the topological homology of BG. But what we did now is a purely algebraic thing. We don't need any topology now to calculate homology. And from this also cohomology. Okay, I'm just skipping through some. Are there any other questions? Okay, Balak, I lied a bit. We will need some topology later, but I have to do some algebra now. This is actually not what I'm concerned about. Group homology and group cohomology. Oh wait, let me just define this as group homology. We can define group cohomology as well. I'm just going to write this like this. We need some coefficients M. It's just the cohomology of the chain complex. What do we do here? We hom of all G module homomorphisms from F to M. And this is the same thing that you know from topology. You just take a normal chain complex and you dual it, and then you get the cohomology. This is actually what happens here as well. This is actually really useful, especially group cohomology is very useful to look at the structure of G. The structure of the group cohomology of G tells us a lot about the structure of G, but we're not done yet. We don't want normal group cohomology. We want Tate cohomology, and this is actually a pretty nice thing. So, okay, I just defined the term resolution. Resolution ends somewhere. What does this mean? We have some Fi. We go into F1, we go into F0, we go into Z, and we go into 0. This is some resolution. But the thing we are concerned about now is a complete resolution. A complete resolution has no end. What does this mean? We have some Fi. We have some other boundary maps. We go into F1, we go into F0. And from there we go straight into f minus 1 and into f minus 2 and so on. And now I might need to draw something. This is not yet what a complete resolution is. We have two more maps. We have maps that look like this. Such that we can kind of make this into two resolutions. So what does this look like? If we look at this left part here, all the modules with positive index and they go out into Z, this is just a normal resolution. And then from Z into F minus 1, this is just a resolution, but kind of backwards. And it turns out that these backward resolutions, if we just restrict ourselves to modules of finite type, is just a dual of a resolution. So as it turns out, that the complete resolution is a resolution plus the dual of a resolution with an index shift. Okay, what do I mean with by an index shift? This f minus 1 is the first term of the backwards resolution. This should be some f0. So we take a resolution, we take the dual of a resolution, shift the index of the dual of the resolution, and we glue these together with the map I just drew, and this gives us a complete resolution. And as it turns out, applying the same procedure as with normal group cohomology, we obtain a cohomology sequence, a cohomology theory called Tate cohomology. It's usually written with an H hat, but I think I can't draw it like this. No, I can't draw it like this. I'm sorry. Just one thing about the structure. This is really important. Is what does the Tate cohomology actually looks like? It actually almost looks like normal homology and normal cohomology, but they kind of glue together in the 0th and negative 1st dimension. This is, I think this picture could maybe illustrate this. This is something I definitely need to draw. So if we have if we take the Tate cohomology of G into module M, this is just the same. How can I? What is this? Okay, this is just the same as the homology of G into module M. Under some condition, if I is positive. Why is this the case? If we look at the positive part of this complete resolution, nothing has changed. This is still a resolution. So if we calculate the group cohomology, then nothing should change. 0th case, because then the last map doesn't go into 0, it goes into some other module. But if this is strictly positive, then nothing is changed. So in the positive rank, this is just group cohomology. And because we have the dual of a complete resolution, that we dual again by calculating group cohomology, but with an index shift, this I've cohomology is just the group homology with an index shift of G in some module M. if I is negative. And by negative, I mean it's smaller than -1. So the real question is, what is the following? What is the 0th Tate homology? And what is the -1st Tate homology? Tate cohomology. This is a big question. Any questions so far? Yes. Yes. Oh, I forgot to mention that all groups are finite. I think I mentioned somewhere that these complete resolutions only work if the modules are of finite type. And we can only get some complete resolutions of finite type if G is finite. And this is why Tate cohomology only works in finite groups. Thank you. And yes, we have these augmentation maps. The augmentation map is this one I drew. This goes from F0 into Z and from Z into F-1. These are the norm maps. And the big question is now, what is H0 and what is H-1? And it turns out there's a norm map. I'm going to define this norm map really quick. There is some analog to Tate cohomology, but as far as I know, this doesn't work with resolutions of finite type. And if you really want to guarantee the existence of a resolution of finite type, you need G to be finite. Because what you want to do here is, if we look at such a complete resolution and that the negative part is just group homology, what we used here is that we can dual twice and come out with a normal resolution. If the modules are not of finite type, then dueling twice gives you a completely different space in general. Yes, so what we're doing here is to calculate cohomology, we take the dual of this part, but this part is already the dual of a resolution. So we take two duals, and this should just get us a normal resolution. If the modules are not of finite type, or if G is not finite, then we get a different space. Okay, we have a very important map, and this is called the norm map. Norm map is defined as a map that sends some, I don't know, some element X into some ZG module. And what does this look like? 1x plus d2x plus gnx, where these g's are just all elements of x. So we kind of look at all the different elements that the G action can take this x and just sum them all together. This is called the norm map. This is a well-defined map from mg into m to the g. I think it's in this direction, yes. mg is m divided by the g action, and mg, m to the g, is the greatest submodule on which G acts trivially. And it turns out that the 0th Tate cohomology of Gm is the co-kernel of this norm map, and the negative first cohomology is the kernel of this norm map. So what does the state cohomology look like now? It looks really weird, in my opinion. It looks like this. We have the second cohomology, then we have the first cohomology, then we have the co-kernel of n, then we have the kernel of n, and then we have first homology, and then we have second homology, and so on. This is a really weird sequence of groups, but it turns out that this is actually a cohomology theory with a cup product. One thing I want to prove directly is the existence of long exact sequences, because this is a pretty important tool. Let M like this. Let this be an exact sequence of G modules, and what we want is a long exact cohomology sequence. Before I draw this one, I just let's look at some questions and leave this window open. Down, wrong. This should be correct. The zero Tate cohomology should be the co-kernel, and the negative first cohomology should be the kernel. Yes, this is correct. This is correct. Okay, so what is the long exact cohomology sequence that we want to get? We want to get a long exact sequence. What does it look like? It looks something like this. Some Tate cohomology in coefficients I. And we go through these groups. And then we go up in dimension. This is actually a sequence which we get from cohomology. And we have another sequence, which is also a kind of standard sequence. It's the one from homology. I'm going to write this one down also. These are the sequence that you get from the group homology and group cohomology. And now I can show you why it was clever to define the Tate cohomology in this weird way that we did. If you don't remember the snake lemma, this might come to a really hard surprise for you. But if we have our norm maps here all the time, we get commutative diagrams. And what does this commutative diagram mean? It means that by the snake lemma, we get a long exact sequence. This long exact sequence has a particular form. the snake lemma, we get a long exact sequence that looks like first. I'm just going to go into here, and now we go down in the dimension, but when we go down in the dimension, we have to look at the co-kernel. The snake lemma tells us that we get an exact sequence if in the upper row we apply co-kernels, in the lower row we get kernels. So so I'm going to write this as n. Then into the kernel. And then we go on with homology. And our definition just told us this is a long exact cohomology sequence of Tate cohomology. Okay, so we get this exact sequence, but this is not all. What we also get is a cup product. I'm not going to go into any detail here about what this cup product looks like, but I'm going to tell you that the obvious way doesn't work. The obvious way is the following. If we have two resolutions, f, and I'm just going to call this v, then the tensor product f times v is a resolution, and we induce a cup product. This is the obvious way to do this, and I'm going to wait like 1 minute here and then let you see where this argument fails. The proof goes in the following. Tensor product is a right exact functor, so it sends resolutions to resolutions. And this is the entire proof of the definition of the normal cup product in the normal group cohomology. And think a minute about this and then tell me why this doesn't work in Tate cohomology. Does anyone have an idea? I'm going to wait a few more seconds if I see something in the chat. Okay, I'm going to spoil the solution why this doesn't work. So the idea is the following. If we have some resolution, where is it? Here, we have some resolution, and we apply a tensor product to it. This is an exact sequence. The tensor product is a right exact functor, and this is a right exact sequence. So we get another resolution. Pretty easy, right? The problem is, if we look at our complete resolutions, this sequence doesn't end anywhere. right exactness of functors doesn't do anything here. We can't guarantee that the tensor product of complete resolutions is still a complete resolution because we need total exactness of the functor, but the tensor product is in general only right exact. This is why the obvious way to construct the cup product doesn't work. There's a way to repair this, but I'm not going to go into detail about this. Oh yeah, but Balaka actually saw it. Nice one. Nice one. Congratulations. Yeah, dimension shifting saves us, but there's the book I used, which is brown, does this in terms of a completed tensor product, and this is actually 5 or 6 pages of completely dry homological algebra, which is not something I want to do here. Okay, now that we have this solved, we can go on. We have some nice properties. This is actually a really nice property. Which is kind of that it is completely determined by the 0th degree. Okay, what does this mean? Formally, for every G and every G module M, there exist G modules N and P with the following. The I minus 1th homology of N is just the normal Tate cohomology of G in coefficients M. This is just rank I plus 1 in some coefficient module P. So we can do this repeatedly to just end up with H0, which means that the Tate cohomology is completely determined by looking at what the 0th cohomology of any group in any module looks like. If we know this one, then we know the entire theory of Tate cohomology, which is pretty strong in my opinion. Can you hear me still? I think my notebook just kind of crashed. I'm not sure. It didn't do anything for like 10 seconds. Kind of. It's lagging a bit. I mean, it's lagging the entire time. But yeah, I think we can finally go into topology again. I think some people who have left or maybe just listening in the background can listen up again. We're going back to topology. Finally, now that we have established what the Tate cohomology looks like, we're going back to topology, and we're going to look at free actions on spheres now. So let G be a group that acts freely on a sphere. I'm just going to call it Sn. The first thing is, what can G actually look like? We have to rule out the even case. For a reason that I'm going to tell you in 5 minutes. Which groups connect on the S2N? The answer is the trivial group and Z mod 2Z. These are the only groups that can act freely on an even dimensional sphere. Why? The proof is pretty easy. If G freely on some S to the 2N, then every FG has to be homotopic to the antipodal map that sends x to minus x. This is just some topology fact that you know. So every fg has to have degree fg, and this is just -1 to the 2n plus 1, which is -1. That means that the map that sends G to the degree of Fg is a group homomorphism. Oh god. From G to the map -1, 1 with trivial kernel. Why? Because every element that is not the neutral element has degree -1. So this means this map is injective and G must be a subgroup with 2 elements. And the only such groups are the trivial group and Z mod 2Z. And so this actually completely rules out any even dimension stuff. Any questions on this? No. Okay. So the thing we actually want to look at is the uneven dimensional case. This argument fails in odd dimension. Why? Well, the degree of the antipodal map is what when it's -1 to the 2n plus 1 plus 1, that is plus 1. So the map that we constructed that sends G to the degree of Fg is just a zero map, and we can draw no further conclusions. And this is where Tate cohomology comes into play. As one thing we do know is that because the degree is 1, it means that this group has to act trivially on the homology. If all degrees are 1, then G acts trivially on the homology of S2n plus 1. -1. What does this mean? We look at any chain complex of this sphere, whatever it looks like. We just take any CW structure on which G acts freely. What does this look like? It looks like it starts with some 0 because we know that S has some finite dimensions, so at some point it has to be 0. And then we have some C to n, and we have some C to n minus 1. And we go down into C0, and then into Z, and then into 0. Okay, this is what the chain complex looks like. But we can actually modify this chain complex in a really nice way. Because G acts trivially on the homology, we know that the map Z into G into C2n I can't write anymore. What's happening? I hate this program so much. Okay, now I can write. Okay, so the map Z into C to N with Z having the trivial ZG structure is a ZG module homomorphism. For this, we need that G acts trivially on the homology. But then this is a ZG module homomorphism, and we can modify the chain complex that we had above to get this chain complex. So we get into Z. This Z just sends the 1 into any cycle that generates the nth homology, which is also Z. So this goes into some to N. Then we have the normal chain complex to C0, then to Z, and then into 0. And then we had what? The 2n minus first homology of S to n minus 1 is 0. And the first map, which we have just constructed, is injective. So we see that this sequence is exact. This is actually a really nice thing because now we can just glue such sequences together. Okay, how can we draw them together? Okay, we have some C1, we have a boundary map into C0, and then we have a map into Z and then out of Z, and this maps into C to N. And this maps into C to N minus 1 and so on. This gives a long exact sequence, and in fact, this is a resolution, a complete resolution. Why is this a complete resolution? Well, we have to just check that the only part we had to check that we have exactness and we have ZG module homomorphisms. What do we conclude from this is that we have a periodic complete resolution of Z over ZG. What do we conclude? G must have periodic Tate cohomology. Any questions so far? Oh yes, thanks. This all goes into 2n minus 1. Thanks. Now it's completely disappeared. Okay, so this is actually a necessary condition for G to even be able to act freely on a sphere. We know that if G acts on a sphere freely, then it has to have periodic cohomology. In the other direction, we can compute the homology of G, and if we see that it is not periodic, then we can completely rule out any actions. Then we know that they can't exist at all. So the final question that we want to answer is which groups have periodic homology? And this is actually only a few groups. So this rules out a lot of groups, and this made some really big progress in the field. The first thing we want to look at, which is kind of the obvious thing, is every subgroup H, we have an inclusion into G. This gives a map, we call it the restriction map, that goes in the other direction. So it goes into, it goes from Tate cohomology of G into Tate cohomology of H. And this is a ring homomorphism, where you consider the Tate cohomology with the subproduct as a ring. What does this mean? This sends invertible elements to invertible elements. This is an important thing because there's some nice classification. It turns out he has periodic cohomology if and only if there exists an invertible element U, the Tate cohomology of G, such that the cup product with U gives isomorphisms. What does this look like? We have some map from the Ith homology, Tate cohomology of G, and this goes into the I plus D Tate cohomology of G. And this map is given by it sends some X into some U cup X. And these are all isomorphisms. What can we follow from this? We follow if G has an invertible element of such type, then so does every subgroup of H, of G. We follow from this, if G has periodic cohomology, then every subgroup must have periodic cohomology. There are some questions. Meta expyrosin palingenesis, what do you mean? Do we get the period in the cohomology as well? It should be n+1 periodic for reaction on Sn, I think. Well, we looked at free actions on 2n-1 spheres, and we saw that this gives a period of 2n. And this is periodic in Tate cohomology. And well, if you look at the structure of the Tate cohomology, then this is almost the normal group cohomology, just in degree 0. It's different. So you can say periodic Tate cohomology is the same as periodic cohomology at degree greater than 0, because the degree 0 is always just Z. Yes. Is it true in negative degrees as well? What do you mean? Is what true in negative degrees? The periodicity, yes, yes. Tate cohomology is defined for all whole numbers. Yes. Yes, this is, oh, you mean the cup product in general. Yes, the cup product is defined for all whole numbers. This is actually a really nice thing. I was actually hoping someone would ask that. Because it has nothing to do with the subject at hand, but it's a nice fact. Cup product works in negative dimension. So what does it do? Let's say in negative n cohomology and some negative m cohomology sends into negative n plus m cohomology. But if we know that the negative Tate cohomology is just the homology with an index shift, and we follow from this that this is a map from nth homology and mth homology into n plus m plus first homology. This is a weird map, but this map actually has a geometric interpretation. I'm just going to link the paper in the chat. This is the paper number on archive.org. Yes, the periodicity isomorphism is given by a COP product all the time. This can also be of negative degree. It doesn't matter. Okay, so we know that every subgroup has to have periodic cohomology. So we have to rule out some groups. So if we rule out some groups that cannot have periodic cohomology, then we also know that a group that has periodic cohomology can't have this as a subgroup. So we want to classify all the subgroups that G can have. There's some examples. For example, from ZP times ZP does not have periodic cohomology. Why? Well, you can do two things. The first thing is you calculate the homology by BG by hand, or you use the Künne formula. Künne formula tells us that the Tate cohomology of ZP times ZP has to grow linearly in rank. If you just calculate this group cohomology, you don't need any other, then you can immediately rule out periodic cohomology, because you see that the rank of the cohomology grows linearly. What can we follow? G cannot have any subgroup of the form ZP times ZP. What does this also mean? Any abelian subgroup of G must be cyclic. This is actually a pretty strong thing. Just from very basic things that we researched about this Tate cohomology, we have some first theorem. We can actually call this a theorem. If G has periodic cohomology, then any abelian subgroup of G must be cyclic. Nice one, Meta. Did you know this already, or did you just find this out yourself right now? With a bit of group theory, we can get some nice other theorems. We can follow something else. This is actually equivalent to the following. Every elementary abelian P subgroup of G has rank at most 1. Well, why does this follow? This follows because any abelian P subgroup is an abelian subgroup, so it can't have rank greater than 1. From this we follow G has a unique subgroup of order P for all primes P. Why? Well, we know if you do some group theory, that one of these groups has to be in the center. And if you have two such subgroups, then you have a direct product of the form which we have here above. And this can't be. So we can only have one P subgroup for any prime P. And what can we follow from this? This is actually now a theorem that we can cite. This is nothing that has anything to do with topology, but it's a theorem that you get if you look at any group theory book. Is oh wait. This is something I had to tell beforehand. The two things we had here is just for P groups. If we have a P group and it has a unique subgroup of order P for all primes P, what can we follow? We follow that P is cyclic or generalized quaternion. This is just a generalized quaternion group. This is a theorem of group theory, and it has nothing to do with topology, but in a minute we will need this at the end. Does anyone not know what a generalized quaternion group is? I think I'm just going to make this as a remark. Generalized quaternion group is a subgroup of the quaternion algebra generated by K and e to the 2 pi I divided by some K. And we know that if G is a P group and it has periodic cohomology, then it has to be either cyclic or it has to be a quaternion group. And if we know these things about all P groups, what can we say about any group G? Any group G, we have G has periodic cohomology. From this, we can imply can you hear me? Yeah, I think it cut out again. I think my microphone just didn't work. At least I have myself in the stream at a very low volume and I couldn't hear myself. Okay, but now you can hear me? Can you hear me? Yes, okay, nice. Okay, so for any group G we can follow, okay, if G has periodic cohomology, then we know any abelian subgroup has to be cyclic. From this we can follow every elementary abelian P subgroup of G has rank at most 1. From this we follow G has a unique subgroup of order P. What do we follow from this? We follow that every P-Zylov subgroup has periodic homology. And this is the big thing that we'll get back to. The main goal, the last goal, prove the converse statement, which is every P-Zylov subgroup has periodic homology, and so has G. And from this we can follow all the above statements are equivalent. Okay. I think the proof, the last goal of the proof I'm going to do in the chat and not in the stream, because this is going to be a huge wall of text. And as you saw, writing anything down in this program is pretty hard. But are there any questions so far on periodic cohomology? Yes, I wanted to do it in the Discord chat. Oh yeah, okay. Okay, so as a quick skim through all the subjects is we asked ourselves, okay, what is a free action on a sphere? Then we saw that we need some theory. We defined the group homology and group cohomology of a group as the homology and cohomology of its classifying space. Then we asked ourselves, how do we get these homologies of the classifying spaces? We see that the standard chain complex is just something that we call a resolution of Z over ZG. And from homological algebra, we can follow that these are actually unique. So by forgetting topology and doing algebra all the time, we can define group cohomology in terms of projective resolutions. And just by saying we take any projective resolution, then we asked ourselves, okay, what about long exact sequences? We get something that's called Tate cohomology. This is in fact not just some useless mind trick that we can do, but it's actually a strong cohomology theory with a cup product. And then we see if we have some action on a sphere, then we get periodic Tate cohomology. And periodic Tate cohomology is really the thing we want to study. And from this, we got some nice properties. But the really important property is this one. The important property is that G has periodic cohomology if and only if any abelian subgroup is cyclic. This is a really strong theorem, and from this we can immediately rule out some nice groups. For example, symmetric groups or any other have abelian subgroups that aren't cyclic. You know, so yeah. Hello? Okay. Are there any other questions? If not, then I'm going to end the talk and do the discussion on the last proof in the chat. Lecture hall, you mean the chat room? Oh, oh yeah, I see. Yeah. Okay. Then thanks for your attention, and I think I'm going to end the stream now. Hello? Oh, okay. I knew that the drawing pad would fail horribly. It was, I think that took like, yeah, actually a bit more than half an hour longer than I expected. Okay, so there's some theorem we want to prove. All cyclic groups have periodic cohomology. They act freely on S1 by rotation by 2 pi divided by some k. And what did you ask? How can cyclic groups have none? But Z2 divided by Z3 has non-periodic cohomology, but every p alpha group has periodic cohomology. That's not true. At least the thing is, there's an isomorphism times Z2 is the same as Z6. The element 1, 1 is order 6 by the least common multiple calculation. No, it's actually a nice question. I was actually a bit stumbled when I read the theorem abelian subgroup of G has to be cyclic, because this depends on the calculation that if a abelian subgroup is not cyclic, then it has some ZP times ZP as a subgroup. These are the same. It's not some ZP times ZQ, but it has to be ZP times ZP. And that this is actually always the case if a group is abelian but not cyclic is actually exactly this calculation that we've done. Okay, so the first thing, I can test now, right? Yeah, don't. Except Whitehead, please. Yes. Okay. So the Tate cohomology has ring decomposition. The ring decomposition is actually pretty easy. But to see why this is the case is actually not that easy. Um, so the Tate cohomology H can be decomposed into a direct sum of Sylow subgroups, and we're going to write them as some with an index p. And this index p means they are all the elements whose order is a prime power p. This is not just decomposition, product of rings. Isomorphism. Not just a group isomorphism. Um, subgroup for some fixed p. Thing is, this H has periodic cohomology, contains an invertible element. We're going to call it U non-zero degree D. Then by some things which I didn't quite mention, but there are some nice facts. As what we can do, we can find a power. Can you hear me? Okay. E being an integer, a to the e equals 1 for all units in C mod. Now we're going to get a bit into transfer map, but you'll just have to accept them. Does anyone here not know what a transfer map is? A transfer map is the talk I defined the restriction map, which is the induced by the inclusion of groups. And the transfer map is a map that goes into the other direction. So which is in some kind the dual to an inclusion or the dual to a restriction, depending on if you're talking about homology or cohomology. One more thing, I can screenshot my thesis on this part, on the ring decomposition. But in order to get this, you need some transfer map theory, which, again, I didn't do in the talk. The idea is that if you have this product of these p parts of the Tate cohomology, you just sum them up, and then you get another element in the Tate cohomology of G, and this is in fact a ring isomorphism. To prove that it's bijective, it's actually pretty easy to prove that it's a bijection of abelian groups. But we don't want this just to be a direct sum, but we want it to be a direct product. And for this, we have to see that this commutes with the cup product. And this is a bit tedious calculation, but it's pretty simple. I can link it to you after that if you want. I need to test something because this is going to look really ugly if I don't test this. you're going to see rendered in LaTeX is exactly the reason why I didn't cover the transfer map in the talk. Because this is going to get really ugly. Well, I know why. Now you see why I didn't want to do this. By res, I mean the restriction map from the intersection of h with g to the -1 into the Tate cohomology of h. These elements are invertible in the Tate cohomology of h cap g to the -1. I don't want to do transfer maps. A cohomology map that is induced by the inclusion of groups. So if you have a group homomorphism H to G, then you get a cohomology map in the other direction. It's a contravariant functor. No, they are elements. Oh, I mean, they are applied to U. They are applied to U. Wait. Like this. But we also know that the last group in which these are invertible, this group has to be cyclic. The invertibility we have just by, we know that U is invertible, and this restriction map is a ring homomorphism. So V and W both have to be invertible. But this group is cyclic, so they have to be both generators of this group. V equals AW for some A. That W to W to the E to the E is invariant. Invariant. With P invariant, I just mean that this is exactly the case, that we have these two restriction maps that look kind of similar, but they go somewhere else, is that they are actually the same element. So we just, out of the group homomorphisms, and we see that this, if we did this with U to the E, then we would just get V to the E and W to the E, and they are the same. And that these two are the same, this is the definition of P invariance. From some other theorem that I couldn't cover. You know that Tate cohomology ring with index P, this P Syloff subgroup has to have an invertible element of the same degree. To the E, S degree DE, G of G, u to the p, u of p, some degree. This is what we have finally achieved. My LaTeX code. Is there some right character? And because we have taken H to be any Syloff subgroup, we know that for every P, P in Tate cohomology group. Okay, we are almost done. What we want to do is, if we get such an invertible element, in every direct product, a tuple of invertible elements is invertible. And so by the ring isomorphism, we want to send this back to an invertible element in the Tate cohomology of G, and thus we follow that G has periodic cohomology. It's because these dp can be different degrees. And we get an invertible element if every element that we put into the tuple has the same degree, but we just take some suitable power. Suitable powers times such that they all have the same degree. So if some of them has negative degree, we just take the inverse. For example, as a power, we can just take the least common multiple of them. And back via the doesn't like white hats. And H, because I think everybody knows now that it's the Tate cohomology. Also, it wants to take everything. Wow. Okay. We just take these powers of this UP that we have found in P-Tate cohomology. We just take suitable powers so that they all have the same degree, and then we just take the tuple of them, and through this ring isomorphism, we send them into the Tate cohomology of G. So we get an invertible element again, because ring homomorphisms send invertible elements to invertible elements, and we follow that G must also have periodic cohomology. And so all the conditions that we have found above are questions. This was really weird in my opinion. Not sure if I'm very comfortable with talks with a drawing pad and keyboard and something. I think the next talk that I'm going to give, I just stand in front of a whiteboard and film myself. I think this is much easier.